Reality is glitchy. It doesn't work the way you think it does. Particles can be in two places at once, and observing something can literally change it. The universe at its core isn't solid, but probabilistic. Welcome to quantum physics, where logic takes a coffee break and weird is the new normal. Quantum physics is the study of nature at its smallest scales, atoms, electrons, photons, and more. It's a framework of physics that explains how the universe behaves when you zoom in far below molecules at sizes close to the Planck length. That's about 1.6 into 10 to the power minus 35 meters. Here, classical physics crumbles, and a strange, probabilistic world takes over that defies our intuition. For centuries, Newton's laws ruled the world. They explained why apples fall, how planets move, how rockets fly. But as we looked closer, especially at atoms and light, things stopped adding up. Light behaved like both a particle and a wave. Electrons didn't orbit atoms like little planets. They were fuzzy clouds of maybe. They couldn't explain why atoms didn't collapse, why hot objects glowed the way they did, or how electrons behaved in experiments. Classical physics had no answer. It was like trying to play Minecraft with a chess manual. We needed a new framework. In the quantum world, you can't predict exact outcomes, only probabilities. Like an electron isn't here or there. It's a cloud of chances until you measure it. Take light. Is it a wave? Is it a particle? The answer is yes. It behaves like a wave in some experiments and like a particle in others. This is wave-particle duality. Same with electrons. They can interfere like waves but hit a screen like particles. Imagine you're both happy and sad, and only when someone asks the right question your mood collapses into one. That's how particles work. It depends on how you measure it. Imagine there's a person trying to kill you. Okay, too dark, but anyways, normally you're stuck. But if you were a quantum particle, there's a chance you'd magically appear on the other side of the wall, without even opening a door. This is called quantum tunneling. When a particle borrows energy to cross an energy barrier it technically shouldn't cross. The wall represents a barrier of energy, and you, the quantum particle, just slip through it. And it's real. This is how some of the semiconductors work in your electronic devices. You can't measure both the position and momentum of a particle perfectly at the same time. The more precisely you know one, the less you know the other. This isn't due to bad instruments, it's a fundamental limit of the universe. At the quantum level, certainty dies. Let's talk about two of quantum physics' strangest concepts: superposition and entanglement. First, superposition. In our normal world, things exist in one state at a time. A switch is either on or off. But in the quantum world, particles can exist in multiple states at once. That's superposition. To explain this, physicist Erwin Schrödinger proposed a thought experiment. Imagine a cat in a sealed box. Inside, there's a radioactive atom with a 50% chance of decaying. If it decays, a poison is released and the cat dies. If not, the cat lives. According to quantum rules, until you open the box and look, the atom is in a superposition of decayed and not decayed. So, the cat is both dead and alive at the same time. Weird, right? But that's how quantum particles behave. Until you observe them, they exist in all possible states simultaneously. Now comes the even weirder part: entanglement. Sometimes two particles become connected, not by space but by quantum information. When this happens, changing one particle instantly changes the other, no matter how far apart they are, even light years away. Einstein didn't like this. He called it spooky action at a distance. But it's not just a theory, it's been tested and confirmed in countless experiments. Superposition and entanglement aren't just weird ideas. They're the foundation of quantum computers, teleportation protocols, and maybe even the next generation of internet. Every great physical theory has a core equation. Newton had F equals ma, force equals mass times acceleration. Maxwell had equations for electricity and magnetism. And quantum physics? It has Schrödinger's equation. At the heart of quantum theory, this equation describes how quantum systems evolve over time. It doesn't tell you exactly where a particle is. Instead, it gives you a wave function which when squared shows the probability of finding the particle. Quantum physics doesn't give definite answers, it gives probabilities. Where is the electron? What's its momentum? You can't measure both at once accurately. And while this seems weird, it works. Every single modern electronic device depends on it. Unlike classical physics, which works great for apples and planets but not at the smallest scales, Quantum physics is universal. Even large objects follow quantum rules. It's just that for big things, probabilities become so close to certainty that it looks classical. So next time you flip a light switch or stare at your phone, remember, behind the scenes, particles are entangling, tunneling, and dancing in superpositions. We still don't know why the quantum world behaves like this. But one thing's certain, it works. And it's beautiful.